So in the last lecture, we talked about how a arbiter or a synchronizer for asynchronous inputs into a computer can actually make the success of that computer in terms of it operating correctly without crashing a statistical thing. And I told you before that this was extremely disturbing to some folks, you know, who think of computers as being these perfect beings, right? That, you know, human beings may have all kinds of strange things, but at least when I sit down at my PC, you know, it's perfect, right? Well, the answer is that it's not perfect. Some of the time it's going to fail. And all that we can hope to do is make the probability of failure incredibly small. Okay, so small that basically we can depend on it almost all of the time. We're going to talk about this a little bit more today in terms of really getting at the essence of something that we call the static discipline. Now, the static discipline is going to talk about the relationship between true and false, 1 and 0, and a really continuous quantity, which is going to be voltage. And the voltage is going to continuously vary between a low voltage and a high voltage, and we're going to make a map right now between voltages and logic levels. Okay. So first of all, most of you guys know about this because you're closer to me in age than most of my students are in most cases. But you know, they have a hard time even knowing what these things are. Okay? You know, if it's not a CD, you know, they've never heard of it. But you know, back when I was in college as an undergraduate, we used to make lots of these, you know, various bootleg copies of music. And of course, every time that you made a copy of an analog tape, what would happen is that the copy was degraded compared to what you were making a copy of. And of course, if you copied it many times, you ended up from a nice, beautiful signal like this, ending up with something with a lot of noise on it. And in general, this was, you know, the bane of all of us in college trying to make free copies of things. And the reason is that noise would get in between the reading of this tape and the writing of that tape and the reading of this one and the writing of that one. Well, the neat thing about digital logic systems is supposedly that they are immune to noise. Supposedly, if you send in a bit stream at the beginning, and there's a little bit of noise in the world, this is a logic buffer here, this little triangle here, which just replicates from in to out, and a little bit of noise is injected into here, and that happens again and again, you still end up with a perfect bit stream, supposedly. Okay, and you, of course, have seen the ads for digital television and so forth, which claim that, you know, unlike this old-style stuff, the copies are, quote-unquote, perfect. Well, we're going to look at that a little bit today and understand, first of all, how the claim is made, and second, why the claim is false. Okay? So, let's begin by actually looking at a circuit which is a CMOS inverter. Now, I introduced you guys a little bit before to the idea of a field effect transistor. You'll notice that there's one over here down at the bottom, and there's one over here at the top. And the one at the bottom, unlike the one at the top, does not have this little bubble, this inversion symbol in front of it. And this circuit over here functions in a way to take an input logic signal that I can draw this in here. The relationship, of course, of an inverter whose symbol looks like this, or if you want to, it's a symbol that looks like this, is that if the input is low, then the output is high, and if the input is high, then the output is low. Now, how does this thing actually work? Well, there are two transistors in the circuit here, and the top of this transistor is hooked to a symbol over here, and that symbol stands for a high voltage. Okay, so let me write that on the board as well, that in a sort of 1980s type integrated circuit, this is a symbol for plus 5 volts. And this is always a symbol for 0 volts, or sometimes it's called ground. Okay, because back in the old days when you had telephone systems and radio systems, you'd actually connect them to the earth because aerial would pick up a signal better that way. There's lots of other reasons, but anyway, you'll often hear this referred to as ground. And the symbol for this is sort of like a stake in the ground. Another symbol you'll sometimes see is a thing that looks like that. That's also ground. It turns out there's subtle differences in between these. You guys don't need to know them. But a symbol like this is meant to stand for the high voltage that's in the system. And typically, a computer chip will run off of a power supply that gives it 5 volts and ground. Okay? It could be a battery. It could be a little box that you plug in the wall, and the output of that is plus 5 volts and ground. And the way that this system works is that these two devices act like switches. Okay? And in particular, let me go forward just a little bit. The switches are built like this, and you saw this in my lecture before. There are two types of transistors. There's the one without the bubble, which is called the N-channel transistor, and the kind with the bubble, which is called the P-channel transistor. And to describe exactly how these transistors work is a one-semester course, but to describe them well enough for us is actually a 1-minute course, which is to say that if I feed a high value into the gate of this transistor, it acts like a switch that is closed. And if I feed a low value into the gate of the transistor, it acts like a switch that is open. Okay? And the exact inverse happens in the case of the P-channel transistor. And again, without having to remember all the colors and all sorts of stuff like that, just think of it, this is a closable switch, which is controlled if you put a high value in here, it closes, and a low value, it opens. Here, there's an inverse, so it's the low value that closes the switch and the high value that opens it. Now, how does this circuit actually work? I'm going to go back one here. Well, think about it. When the input is high, which of these two switches are going to be closed? The bottom one or the top one? When the input is high, the bottom one is closed. So the output will be connected to ground. In other words, the output will be low, because ground is the low value. When the input is low, which of these two transistors is going to be closed? The top one. So the output will be connected to plus 5 volts, which in this case is what high is. Now, just an aside, modern computer systems operate on less than 5 volts. Some of them operate on 3.3 volts, some of them on 2.2. The trend is down, lower and lower and lower. There are some that do 1 volt now, and even some that do 0.6 volts. Okay. And it turns out that by lowering the voltage of the system, it doesn't have to use as much energy to switch from one state to the other. Okay? And what that means is that A, you can switch a little faster, and B, you can switch without dissipating quite so much heat. The amount of power you use goes down. However, for a reason that you'll see, we're going to start with this for now, this plus 5 volts, which is where things were in the 1980s. And still, actually, most of the chips that are in the peripheral cards that are in your PC, the video card and all sorts of things like that, typically run on plus 5 volts or 3.3, whereas the stuff inside the processor tends to run at the lower voltages. And the C stands for complementary. A-R-Y? O-R-Y? A or O? Good, thanks. I can't spell worth a damn. So. But there's complement and complement, but I think that is right. What it means is that, first of all, in the old, is that right?
Unless you really like it. Yeah.
That's actually wrong. Oh, this is if you give someone a compliment, right? Is that right?
More likely right.
Okay, well,
Depending on what it's supposed to mean.
that's absolutely right. Okay, I think. In the 1960s, when they first made these types of field effect transistors, they made the gates out of metal. Okay, so the structure. Let me go to the picture of the cross-section of what one of these transistors looks like. Here's the gate, this red thing here. This was made out of metal. And then there was a layer of silicon dioxide, which is the oxide. And then there was semiconductor down here. So it was called metal oxide semiconductor. And the name has stuck despite the fact that this gate is no longer made out of metal, but is made out of a certain thing called polysilicon, which is yet another type of semiconductor that's put on there. So it's really a semiconductor oxide semiconductor device, but the old name has stuck. So this is a MOSFET, a metal oxide semiconductor field effect transistor. And CMOS means that we use both types of them, the complements of each other. One's the P type and one's the N type. Thus CMOS. No matter how it's spelled. Okay, so in general we have a circuit that we can use to build an inverter. Now this circuit has characteristics that I can feed it not only low values or high values, but I can feed it intermediate values as well. And we've been talking about what happens when a wire is in transition from low to high or from high to low. And what I want to do right now is I want to begin digging a little bit deeper and saying, what happens if I do give it a voltage that's somewhere in between a 0 and a 1? What does the circuit do? And the answer is that if I were to plot, and I'll do that right over here, the action of a circuit like this as input versus output, and you saw this a little bit, this is going to be V in, and this is going to be V out, like so, and this is going to be 0 over here. If I feed in a low voltage, we said a high voltage is going to come out. And for the sake of the discussion, let's call this 5 volts, and let's do this thing up to 5 volts too. And as I slowly increase V in, I know that eventually V out is going to end up down here near 0 volts, because if I feed in high, I get low. If I feed in low, I get high. And somewhere in the middle, the circuit is going to make a transition from one to the other, like that. Okay? So if I were to measure the input-output relationship of an inverter, I'd get a picture that looks like this. Okay? And this picture has the following characteristic. For voltages on the input, and that's what's represented by this left-hand side, ranging from 0 volts all the way up to 5 volts, this range of voltages that is fairly large, near 0, those all map to a range of voltages on the output, which are high, and that range is smaller than the range I began with. What I'm trying to say is that the slope of this transfer curve, here's in and here's out, that this slope is less than 1. In other words, the amplification in this region here has an absolute value of gain less than 1. It's pretty much a horizontal line. Okay. In other words, for voltages, if I were to send in a sine wave as input here, what I would expect to come out is a sine wave that's much smaller. The gain is low. It's attenuating the amplitude of the input to the output as long as the input is within this range. In a similar way, inputs that are within a range over here that I give it result in an output which is also very small. Okay, so you notice in this picture the way that I've drawn it is that this large gray box over here near an input that's high maps to an output range which is smaller. Okay? And then finally, yeah?
Is the reason that there's any leak through at all because as voltage gets higher, the other gate partially opens? And
That is basically true. In this region over here, we mostly have one transistor being on. And in this region over here, we mostly have the other transistor being on. And in this region in the middle, we have both of them being on. And that's actually what I was just going to say. So remember, there's two transistors in the circuit. There's the P-channel FET, and then there's the N-channel FET. And they're both connected to Vin. And here's V out. And here's ground. And if this is high, this guy's on and this guy's off. So the output is connected to ground. If this is low, this one's on and this one's off. So this one is connected to plus 5 volts. And this one is off. But if it's somewhere in the middle, both of these transistors are going to be on. And this output is going to be some mixture of 5 volts and ground. And I'll leave it to your son to talk about how circuits like this work. But you can kind of understand, if you think about these as 2 valves, and there's water here, right? That this is letting the water in and this is draining the water out. That if both of the valves are on, some of the water is going to go in and some is going to drain out, but you'll be somewhere in the middle. Okay? And that's the region here. Yeah.
Are the gates either open or closed, or is there an intermediate state?
There is an
for the
intermediate
gates
state where
themselves?
they're in the middle.
Okay.
Okay? Yes. So, and that's this range here. And in this range here, it has the characteristic, and I'll use a triangle wave to differentiate it from here. If I feed in a small waveform here, I get out a big waveform here. Okay. Fundamentally, this is what's called a nonlinear transfer curve. If this was a straight line, no matter where I was along the input space, the gain, the amount of amplification that I get, would be the same. But it's not a straight line. It's an S-shaped curve. So in this part of the curve, the gain is less than 1. In this part of the curve, the gain is greater than 1. And then in this part of the curve, again, the gain is less than 1. And this is the fundamental characteristic of all logic gates that we're going to talk about. Gain is the absolute value of the slope in the region. Okay? Sort of an idea of what the volume knob is set to. The higher the knob, the bigger the gain is. So the radio station sends you a signal which is a fixed loudness, and you get to say how much gain you want before it gets to your ears. Okay. Now, why do we do this? Why is this a good thing to do? Well, let me ask a question. If I took the output of this inverter and I fed it to another inverter, what can I now afford to have happen that I couldn't afford before if there was no gain change at all? Well, if I send a signal which is closer to ground, then I can afford, before this thing hits the next one of these things, for a little bit of noise to be injected and to perhaps contaminate this signal by driving it a little bit more towards the middle, because I know that this gate is willing to accept a bigger range of inputs than it will produce on the output. Another way of thinking about this is in terms of the quality of the signal. The quality of the low and the high here are fairly low. In other words, it's okay for this to accept a value and for it to be called low, even if it's pretty close to the midline. The quality of the output, however, is greater than the quality demanded of the input, and that it's going to push the signal out from the midline and say, I'm going to make it more clear whether it's a low or a high. I'll take a signal that may be closer and I'll turn it into a set of signals that are more towards the edges. Therefore, I will improve the quality of the digital signal that I'm given. And that will allow me, before I hit the next stage, to inject a little bit of noise into the system and for that noise to be rejected by the next stage. Okay, we're going to talk about this over and over again. So here's what the transfer curve looks like. And I'm going to mark it in terms of 4 different symbols. One set is going to be called the input thresholds, and the other set are going to be called the output thresholds. Notice this is VIL for voltage input low threshold. And this is VIH, which is voltage input high threshold. And notice that these two are closer to the midline than these two over here, which is the output thresholds. And this is VOL for output low, VOH for output high. And notice that those are further away from the midline than the other ones. And again, here's the S-shaped transfer curve that we're going to have of low gain, high gain, low gain. And what that will mean is that a signal that can be anywhere up to here will be translated into a signal closer to the edges. Maybe there's an even better way to say this. Let's say that you get in the mail a carbon copy which has been done through 20 sheets of paper, right, back in the old days of carbon paper. And you get it and you can barely read it, right? And you're asked to send out, to retype a new copy of this thing and send it on. What you're effectively doing is functioning as this kind of logic device here. You're willing to accept input that has degraded, where it's hard to tell the difference between where the ink is and where the ink is not. And then you're going to produce an output which is more clear by retyping the letter and sending it out. All logic gates do this. They all improve the quality of the signal that they get and send out a higher quality version. And the way that you do that is that, let's say this is the range of brightnesses of the signal that you get, where this is, dark and this is light. Okay? If you're doing a copy of a document, you're willing to accept anything that's less than this much as being dark and anything that's more than this much as being light. Let's say in here you're not sure. And then you're going to generate an output that's cleaner than the input that you got. Now typically you're going to just make dark be dark and light be light, so you're going to function as a buffer, not as a inverter. But your output curve will look something like, well, like this, an S-shaped curve. In other words, as you look at this cruddy piece of paper you're making a copy of, anything that's pretty much dark, oh, I have a better example. Perfect example. You have this ballot, okay? No, this is absolutely right, okay? What did you hear about them doing, supposedly, okay, in Florida, some of the ballots? They were knocking off the chads, right? In other words, if they got a ballot and only half of the chad was gone, they'd kind of pick the rest of the chad off and feed it into the machine. What were they doing? They were improving the quality of the information that they were getting, right? Pushing it more towards the edges, okay? This is no chad, this is chad, okay? But they were willing to accept information that was closer to the middle, okay? The pregnant chad, do you remember, And they were saying, okay, no, we should push these more towards the margin. In fact, the entire election dispute is about signals that have been contaminated by noise and are too close to the middle to figure out whether they're a 0 or a 1. This entire thing is about zeros and ones, right? The chads are supposed to be zeros and ones, and there are some that are close in the middle, and the machine is insisting that the quality be higher than people are able to discern, supposedly, depending on which side of the debate you're on. I'm on the side that says count them all, but anyway, that's because I know about this stuff. And of course, my political leanings have nothing at all to do with thinking about this.
So who invented those voting machines?
I think it was Hollerith or something way back. Oh, no, it had nothing to do with MIT. No, it's an awful thing. No, I think punch cards began as a way to program looms, how to do automatic weaving. Okay, so you'd have these, and they were made out of wood with big holes drilled in them. And it's easy for the machines, right, but it's not good for people. And so, unfortunately, the voting machines have been made so that it's easy for the machines to count, but not necessarily easy for people to, generate these things. Now, who would ever think that a vote should be based on a piece of paper that's held by, tiny little pieces of paper to the side and perhaps punch through, but if you kind of rattle the thing too much, then it falls out, and, it's just nuts, right? So anyway, don't ever do this, okay, when you're designing a system. We should get a lecture by one of those guys that knows a lot about this. But there was an article about how bad this is. And it's one example of saying, let's design the system because it's easy for the machine to deal with it, not because it's easy for the people to deal with it. So it's a real shame. But anyway, back to this. Do you guys understand this business of improving the quality of a signal? Okay.
Did we talk about how it does that yet? How the semiconductor?
No. And actually, we are not going to talk about it, because it turns out that in order to understand that, you need to understand what the individual transfer characteristics of a field effect transistor are in terms of their current versus the voltage on the gate and stuff like that. That's actually a little bit too far for this course. It's okay if the transfer curve lies anywhere within the region here. what the gate guarantees you, what the static discipline guarantees you, and this is just the same as a programming discipline, is that for any voltage less than VIL, an inverter will produce a voltage greater than VOH, and for any voltage greater than VIH, it will produce a voltage less than VOL. And for voltages in between here, all bets are off. It can do anything that it wants. Okay? It could even have a transfer curve that goes up and down. It really doesn't matter. Okay? But these are the constraints that it has on the thing. Okay? And when you open a logic book or when you're designing a circuit like this, you will get the specifications for these four values, VIL, VIH, VOL, and VOH. And it will always be the case that the distance between these two will be greater than the distance between these two, because every logic circuit will improve the quantization of the signal by pushing things out towards a stronger high or a stronger low. Alrighty. I think we're all getting it here. Now, in general, it is difficult to build a buffer, something that just transfers. This is wrong. I don't know why this is here. This is the table for the inverter. The table for a buffer is low goes to low and high goes to high. It turns out the way that you build a buffer in CMOS is just to chain two inverters together. So you take the inverse of the inverse, because in CMOS there's no easy way to build something that just is a logic buffer. So it's built like this. Yeah, it's a great idea, but it turns out that it doesn't work for called effect, and I'm not going to talk about that. Okay, so let's not worry about it. But the buffer is actually somewhat easier to explain because there's not this crossing of the values from low to high and high to low. And so here you can more easily see the way that we take a perhaps more lesser quality signal on the input, and we compress the values to become a higher quality lower high on the outputs. And that this compression is exactly the same as saying that the curve has to have this S shape to it. Because notice, this needs to expand. The gain in the middle region needs to be more than 1, and the gain in these two regions needs to be less than 1. And so that non-linearity, the S-shaped curve, is extremely important. And there's the constraints on the buffer. Yeah?
So I missed your discussion, but I'm not exactly clear on what the buffer
Oh, on what the buffer is?
Yeah.
The buffer just passes low to low and high to high. It's called buffering the signal because the output is, the data flows one way and it stops the output from affecting the input. But that's besides the point, okay? So just assume that it's just a word, okay? What it is it's a logic function that seems to do nothing. But what it does do is it improves the quality of the voltage that's being used to represent the low or the high.
So if you had just had one of them, then you would actually get a flip in the value?
You do not get a flip in the value. The inverter gives you the flip in the value.
Oh, okay.
The buffer does not. Okay.
Then the buffer is just two inverters.
And in fact, inside of the buffer are two inverters in series with each other.
The buffer gives you a delay, right?
There is a delay due to the buffer. Yes, that's true. So here's another way to look at it, which is that here again we have an input signal here down at the bottom, VIL and VIH, and here's an output signal over here. And what's nice is that if I know that the signal that's coming out of here is to the right of VOH, which is what the static discipline says, or to the left of VOL, in other words, less than VOL or greater than VOH, I can afford for some noise to come in here and spread the signal out and allow it to go lower up until it hits VIH. So this system becomes immune to that noise because I know that this is a valid input, even though it's composed of this valid output of higher quality plus some noise that has degraded it before we take a look at it.
So what is TX and RX?
The transmitter and the receiver.
Okay.
TX is for transmit and RX is for receive. And if you guys were ham radio operators from the 1950s, you'd all know that. But I guess you're not, so that's okay. Okay. The difference between VOH and VIH is called the noise margin. How much noise we can afford to have contaminating a signal between an output and an input before the signal gets confused. And so this is a margin of the amount of noise we can tolerate in between our gates. And usually the noise margin is made to be approximately the same on both sides. Back in the 1970s, this wasn't true, but in most modern logic families, the noise margins for highs and lows are approximately the same. Now, the region in the middle, where we're in between VIL and VIH, where maybe there's the slightest dimple on the ballot, okay, is called the forbidden zone, okay, like from some space movie, right? And the idea in the forbidden zone is that we cannot depend on knowing what the value is at all. It's not forbidden in the sense that the voltage may not be there once in a while. Certainly when a voltage has to transfer between being a low and a high, it needs to go through the forbidden zone. But what we're trying to say is that our signals in our system will never statically generate a signal that's in the forbidden zone. We expect all outputs to be either here or here, and we expect all inputs to be either here or here once the noise has gotten to them. But we do not expect statically that our circuit will ever have a signal inside of here, because we can't discern whether that's a low or a high. Dynamically, it will go through there, but statically, it will not. Yeah?
How come data flow is going down? It almost looks like you have a big, it's like you have a ballot, you improve the quality, so the data flow, I always imagine going up.
Oh, well, the idea here is that this is the transmitter, and noise gets in, and then the receiver picks up the signal plus the noise. Let's think of it this way. This is the mind of the voter, and this is the ballot, okay? And somewhere between here and here, the voter was thinking about something else and didn't push the pin all the way through. And as a result, we got a noisy ballot, okay? But what they're talking about, what the Gore camp would say is, it's okay if the ballot is more noisy than the perfect voter would have made the ballot, because you can still tell. Okay? Yeah.
You said in the forbidden zone all bets are off, right?
All bets are off in terms of what we interpret the value to be, yes.
But then if the forbidden zone produces something in the two ranges of then how will you know that?
Oh, from the output of a gate, how do
Yeah.
you know if the input was in the
Exactly.
forbidden zone? The answer is you don't. Okay?
Unless it was in the forbidden zone that it comes out. I mean, if it comes out in that middle range, you know.
Then you know, but once it's processed, it may not. So the forbidden zone inside of here, for instance, it may be the case that the forbidden zone is in between these two places, and maybe if you're right here, it still makes a value that looks like a low.
Right.
And in the forbidden zone, it would be okay for this curve to go up and down like this, okay? In which case you certainly wouldn't know from the output whether or not. So, once the people have tallied the votes that are noisy, even ones that are in here, you can't tell whether or not the votes were really noisy. So, okay. The consequence of the static discipline is that the transfer curve has to fall either like this or like that, depending on whether it's an inverter or a buffer. And what it means is that the device must have gain in the middle region, which is positive gain more than 1. And it also must be nonlinear, which means that it has to have gain less than 1 in the two other regions over here. So we've learned that. We sort of understand how it is that now the digital systems can reject noise better than an analog system can. The whole trick in an analog system is to make it as linear as possible. You want that output tape to have a linear copy of the input tape if you're doing an analog tape-to-tape recording. In a digital system, we introduce a nonlinear transfer curve with the specific desire to reject noise, and to reject noise categorically. Okay? But the question is, does it always work? Now, the people who will sell you the digital, the DVD discs and all this sort of stuff will tell you that it's perfect and that the copies of a DVD are a perfect copy and so forth. But the answer is that it ain't necessarily so. Because it turns out that this static discipline, this abstraction, saying that we can translate between voltages and ones and zeros in a perfect way, is in fact a probabilistic abstraction. Okay, and it all has to do with the noise. So I'm going to back up a few cycles here, right to here. Let's take a look at this noise. What's the assumption that's going on here? The assumption is that the noise is bounded, right? That the noise is not going to be big enough to kick you over to here. But is noise actually bounded? Is noise bounded?
As you ask the question, the answer is no.
Of course not. Noise is not bounded, okay? Is the probability that in another 5 seconds, all of the molecules of air in this room will suddenly move to the corner right here and will all choke to death? Is the probability of that 0? No. Boy. Time to get worried.
Because we have an epsilon.
We need to study faster. We have an epsilon. We have a number very, very close to 0, okay, but it's not 0. And in fact, the electrical noise that influences a circuit is composed of 2 parts. There's one part of the noise, the vast majority of the noise inside of a computer is self-generated noise. It's the effect of what's called crosstalk. In the old days, when phones weren't made and the wiring systems were not made very well, you often would hear a conversation that wasn't yours on the phone. And the reason is that the wires went past each other and the balancing wasn't quite right. And so you got to listen in on, very faintly, some of the conversations that were running on wires near to yours. And that was called crosstalk, because the talk crossed over from one to the other. Most of the noise inside of a computer that the gates have to deal with is crosstalk. So the gates that have to do with the display get a little bit of a signal from the gates that are dealing with the disk drive, okay? Because they're near each other, the wires go near each other, the power is the same for both of them, and most of the noise is like that. It turns out that inside the computer, the crosstalk is in fact bounded noise, because the gates having to do with the disk drive are switching between, let's say, 0 and 5 volts at a known rate, and they're a certain distance from the gates having to do with the screen, and that will generate a finite amplitude of noise, a known fixed amplitude of noise. But this self-generated noise, even though it's by far, on average, the biggest component of the noise, is not all of the noise. There's also other noise which has to do with thermal effects, okay? And the fact that the temperature is not 0 in this room, and that there's some randomness to it. The electrons suddenly go one way, then they go the other way, and then they go this way and they go that way, like the molecules in the air are bouncing around. And that noise is what's called Gaussian noise. Okay, it's actually many different types, but one of the types is Gaussian noise. And many of you know about a Gaussian curve. It's sort of this bell-shaped curve that kind of looks like this, right? And the most likely value that a voltage has, if I put out 5 volts on a wire, let's say this is 5 volts, and that's what's getting transmitted, what is received is something that looks like this. And you know, this might over here be 5.99 volts, excuse me, 4.99 volts, and this over here might be, 5.01 volts. So we're talking about a very small amount of change, but it turns out that these tails, okay, never quite hit 0. So therefore, the probability that we'll go all the way down to, and I'll draw a line like this, to 0 volts is not 0. It's possible that all of the electrons in the system will suddenly decide, hey, let's all go over to the left. Okay? Not that they're making up their minds, but they're moving around at random, and the probability is non-zero that everything will go to one side. And so, in fact, while crosstalk is bounded, the thermal noise in a system is not bounded. And there is a probability, not 0, that this noise will force the system all the way over to that side. Okay? So it's, again, a probabilistic assumption about the noise. And so it turns out that your computer does have a non-zero probability of failing because the static discipline will be violated the same way that it had a probability of failing because of metastability. It turns out that not only is it the case that it might fail because of noise like that, but the parts may suddenly go bad as well. Okay? Now, parts, the reliability of a part typically follows this thing called a bathtub curve. So here's time, and almost anything that you buy works like this. This was first observed, I believe, in light bulbs. that the probability that you have a failure of a part, that the part stops working and never works again, kind of looks like this. Okay? And again, depending on the specific part, the exact shape of this curve will change. Okay? And these have some gruesome names. This one's called infant mortality. Okay? I'm sorry, but you know, those of us that have kids, for us that's a very bad word. And this is when the part is being used, and this is called wear out. Over here. Okay. And so when you buy a computer, there's a good chance in the first few months that you use it that something will go bad. If it has managed to survive the first few months, chances are it'll work for many, many years. And then after a while, the fans and the disk drives and all that stuff will start to wear out and make all kinds of sounds, and then it'll go bad again. And then it's time to get a new one. Okay? And every part inside of the computer acts like this. But what I want you to notice right now is that this curve never hits 0. And certainly the integral of this curve is not 0. And so not only can we not depend on the voltages staying the way they should be and obeying the static discipline, but probabilistically we can't depend on the parts never failing. And so the computer may suddenly stop working no matter how good a job we did making it. Okay? Well, the key that we use in designing computers in general is that we know roughly that the bathtub curve like that means that a computer should basically last for 10 years or so without having a failure on average. Okay? For the military, they make it a little better than that. They say it should last 100 years without a failure. Now, that doesn't mean that they really expect to use them for that long. But if you design a computer for an average life of 100 years, the chances that it'll fail in the next year are very slim. Okay? And so the way that we measure the impact of all the other probabilities is against numbers like these. So if the parts fail once every 100 years, then as long as the static discipline fails less frequently, the failure of the parts will dominate the failure of the system. And the same thing is true with metastability. If we assume one failure every 100 years, we're okay. And so throughout all the design of these computers, those are the kinds of numbers that we use. Okay, this is fun stuff here. In 1997, I read an article which the cover looked like this with this rat, which has nothing at all to do with the topic. But if you get this, it's really fun to read this. As I told you the last time, the age of the universe is around 10 to the 10th years. This is a thing talking about the probability of weird things taking place whose probability are not 0. So if a bird was pecking randomly on a keyboard, it takes him 10 to the 3 million years to write the hounds of the Baskervilles, okay? Which is a long time. So the probability of the bird pecking right now coming up with something is low, but it's not 0, okay?
He probably writes a lot of other great things though before it finishes.
That's probably true too. A full beer can, this is even better, sitting on a level steady table, and this is of course very highly dependent on our current theories of physics, okay? But anyway, according to current quantum theory, a full beer can, and it has to be full of course, on a level steady table will spontaneously topple due to quantum fluctuations about once every 10 to the 33 years. Okay, so the probability of it falling over in 1 year is 1 over 10 to the 10 to the 33. It is a very small probability, but it is not 0. Probability of a mouse living on the surface of the sun for a week, and here we have the mouse, but it's actually a different article, is about 1 in 10 to the 10 to the 42. Okay, now this is a very, very small number. And then finally, the best one of all, the probability of you suddenly dematerializing on Earth, materializing on Mars, then rematerializing on Earth is about 1 in 10 to the 10 to the 51. And again, this is based on very speculative ideas of modern physics, but it might suddenly happen that suddenly my molecules suddenly decide to all go to the sun and then back here. It might happen. Yeah.
I'd like to see the equations they use.
I would love to see it too. If you read the article, I don't think it actually tells you, but there are references to other articles where they actually figured this stuff out. Okay. I put this up not because I want to teach this to you, of course, because it's pretty useless, right, to know this stuff. But to explain that computers are not perfect, and it's okay. That's the key. It's okay.
Like when you copy a CD, how many errors do you usually get?
So that's a great question, and I don't know the answer to that, but CDs themselves have things called error-correcting codes. And part of the idea is that it can tolerate a certain number of errors and then fix the errors on the way back. And we're going to be talking about that in not the next lecture. Well, I'm not sure. It may be the next one or the one after. So we're going to talk about how you can build a system where you're trying to communicate perfect data, and some of the bits will get changed. But by sending some redundant data with it, you can figure out how to fix it back.
That applies to
Well,
today as
it is effectively perfect, but there's still a probability that that will fail too. And in fact, what a CD does, if it does fail, is it tries to generate a sample that's in between the sample before and the sample after, because it assumes that it is music, and to your ear, if you get a little bit of a glitch like that, you won't hear it very much. So, yeah.
Why is there such an astonishing difference between how reliable computers should be as how reliable to the end user and that the average PC actually is?
Well, okay. It's mostly software. Okay, I hate to say it, but it's really the fault of Bill Gates, okay, and all of his brethren there. Most failures in computer systems, the vast majority of the failures that you see are software failures, that the software was written wrong. And there's a bug in the code that is exercised every once in a while depending on exactly the state that you're in and what happens when. When there's a hardware failure, it's usually due to the fact that the manufacturing was not as perfect as it could have been. Not the chips themselves that fail, but the board on which the chips are placed, the way the chips are attached to the board, things like that. It's usually the wires in between the chips that fail. But that doesn't fail nearly as often as the software fails.
What if your computer gets hit by lightning, as did mine?
Wow. Well, see, the probability of that is not zero. I don't know what that means, but we can brush it under all this other stuff, just saying, you know, that's life. Okay. I want to go through something fairly fast because I think this will be pretty easy for you now, before we're done. Actually, do you know what I'm going to do? Let's see. We've been going. When did we start this thing? Did we start around an hour ago? At 11. Oh, okay. So we still have time. Here's a NOR gate. Okay, a NOR gate works just like these inverters work, except it's a little bit more complex. Instead of one p-channel or sorry, n-channel transistor on the bottom, we have two. So if A is high, this transistor turns on and pulls Q low. If B is high, this transistor turns on and pulls Q low. So if either A or B are high, Q is low. If either A or B are high, Q is low. If A and B are low, then these two transistors are on. They're two switches in series with each other, and this high voltage is connected in series with those two of them to the output. And so a NOR gate is implemented like this. And so that's this case right here, where it's high.
So that is actually how it's done.
I didn't.
think that's actually how it's implemented?
This is exactly how it is done. So this is what a NOR gate looks like. Very, very simple, but nice. What's beautiful is that the complement to that, spelled the right way, I hope, is a NAND gate. You put the parallel transistors on the top and the series transistors on the bottom. So if A and B are high, then Q is going to be low. If A and B are high, then Q is going to be low. And in all the other cases, if A or B are low, then Q is going to be high. And so it works like that. I think it's really very beautiful stuff. Now, let's talk about how to implement a logic function in a systematic way. We talked before that I could implement an adder by just having a table of all possible combinations of the inputs and what the result would be. I can also implement an adder or any other logic function as I can implement any logic function as a table, and here's how I would do it. I would start with a decoder like this, and I would feed the inputs, the K inputs, into here. And if you remember, what that did is it selected one of these Q outputs to be high and all the other ones to be low. And let's say I fed a high value into here when this was true. So this k gets decoded into 2 to the k possible outputs, and only one of them is chosen. If I want to implement a logic function that's not as simple as a NAND or NOR, all I really need to do is take a decoder like this, feed in the inputs for the adder that we did before. It was C sub I, A, and B. That decodes those 3 bits into 8 possible outputs, only one of which is going to be high depending on C sub I, A, and B. And for each one of the cases where I want the output to be 1, I just take that case and I run it to an OR gate, and then the output is high whenever that case is true. So for instance, let's say that this was going to be S, and I wanted to say, okay, when C sub I is 0, A is 0, and B is 1, I want S to be 1. I would just take this wire, which corresponds to C sub I 0, A 0, B 1, and I would run this wire to this OR gate. And that would ensure that when that condition is true, this one is high, thus this output will be high. And for each one of the cases of a 1 in the output, I would route a wire from one of these 8 outputs of the decoder into this OR gate, and I'd have 4 wires going into here, and I'd get the output. And I could do the same thing for C sub O down here by taking these 4 cases, this one, this one, this one, and that one, and running wires from there into the OR gate here. So here's one way of implementing arbitrary logic. It works fine as long as the number of inputs is not too big. What happens if the number of inputs is large? Well, the number of wires here goes up with 2 to the number of inputs, and so that can get out of hand. Let's talk about a general way to implement NOR gates. We showed you the CMOS NOR before. There's another type of circuit which is called an NMOS NOR. NMOS stands for N-channel MOS rather than complementary MOS. And it's a system that only has the gates on the bottom, not the gates on the top. And instead of the transistors on the bottom, not the transistors on the top. And instead of the transistors on the top, we replace that with what's called a resistor. And what the resistor is, you can think of it kind of like a spring. It kind of looks like a spring. And what it does is it says, in the default case, if none of these switches are closed, pull this wire up to 5 volts, like a spring trying to pull up to 5 volts. So the Q output here, if all of these transistors are off, the switches are open, the Q will be high. If one or more of the transistors are on, in other words, if an input is high which closes the switch, then the wire will be pulled down to ground. So the Q is low if any of these things is high, or Q is the NOR of any of the inputs, the negated output OR of the inputs. What's really wonderful about this is it's an expandable circuit. I can start out with a NOR of 3 inputs, A, B, and C, and I could add more of them by just adding more transistors and connecting them to this wire. And so I can expand this as long as I'd like. In a regular structure, which basically has a pull-up resistor like this, and here's the output, and here are the inputs coming in horizontally, and whenever I want to include a particular input in the output, in other words, I want to OR it in, or NOR it in, I place a transistor between the input and this wire, which is commonly used for the output. What I'm trying to do here is to show you how to implement the actual NOR gate. So instead of sending a subset of these wires to an OR gate, what we're going to do now is we're going to implement this NOR gate with transistors. Now, where should I put a transistor? Well, when A is true and B is true and C sub I is true, that's this last case here, I would like the output to be high. Well, I can't do that, unfortunately. I know how to implement a NOR gate with transistors. I do not know how to implement an OR gate. But I'll do a trick, which should be clear, I think. Here's the decoder. 1, 2, 3, 4, 5, 6, 7, 8. 0, 0, 0, 0, 0, 1. And here's C sub I, A, B. Okay? When all of them are true, I'm going to put a transistor here. And what it's going to mean is that when this is high, it's going to pull this wire down. By default, I'll try to pull it high, but of course when this transistor is on, it'll pull it down. And then, what should I do to this output to get the high value that I want in that case? I'm going to invert it. And here's output, which in this case is C sub O. C sub O. So there's one part of C sub O. What's the next part? Oh, those are missing all their bars. I'm sorry. Well, what is true? When do we want to have a carry out of this thing? When two or more of the inputs are high, right? So we want to do one here. Goes like this. We want to do one here. And we want to do one here. So I've now implemented the logic for carry out by placing transistors at the junctions of the output of the decoder to generate C sub O.
Now, couldn't we just put the transistors on the other ones and get rid of the inverter?
Yes,
So it's going to
that actually would work too.
drive it high.
Very, very smart. What he said was that instead of putting the 4 transistors here and putting an inverter here, I can put the transistors on the other 4 cases and not bother with the inverter at all. But it's a little bit easier to think about this, I think. So, okay. What this thing is in fact a read-only memory. This is a read-only memory which has 8 locations that are 1 bit wide. This is really, if I get rid of the fact that these have meaning, and I get rid of the fact that this has meaning, and I call this out, and I call this an address, A. Actually, let's call this a data, D. What have I just done? I have a memory with 8 locations in it. And I can put a number between 0 and 7 in here, which will select different rows. And if I select a row with a transistor on it, that transistor will pull this wire low, which will then generate a high on the output. So I have written into the memory with these transistors which places should generate a 1. And so really what this is a read-only memory. Input is the location to read. Here's the data that I get out. And so this is just showing how a ROM can be used to implement logic functions and what the architecture of a ROM is like. It turns out that this is really the general form of a way of programming logic without having to do individual AND and OR gates. This circuit over here is commonly called an OR plane. Okay? And the reason is that you may have a ROM with more than 1 bit in it, in which case there'd be sort of a 2D structure of OR gates here. They're really NOR gates that have their output inverted, but that turns them into OR gates. Instead of decoding all of these cases here and having to waste these other 4 wires, I could replace this structure here with an AND plane. So instead of doing this, what I really want to do is into here I want to have an AND gate with 3 wires on them, and another AND gate with 3 wires, and another AND gate with 3 wires, and another AND gate with 3 wires. And then I want to feed those into signals and their inverse, which is what we talked about before in terms of any logic function being implementable in what's called sum of products form. So you would feed inputs and their inverses up wires like so. Then you would have circuitry which would implement AND functions on some of the inputs and their inverses. Those product terms would come across the middle here and then go into an OR plane which would OR together the appropriate outputs of the product terms to generate the outputs that you want. And if you do that, then you can implement any logic function that you'd like in sum of products form. So in fact, there are certain general circuits called PLAs. PLA stands for Programmable Logic Array, and they look like this. There's an AND plane, and there's an OR plane, and into the AND plane we feed the inputs and their inverses, inverses. You put a symbol like this, meaning I want to include this term in a product, and I want to include this term in a product, so this and this will get put out on this wire, and then that product term or this product term will be included on this output wire here. And so this is nothing more than a regular structure for doing sum of products form for general logic. The way we actually implement this is interesting. We've already seen how to implement the OR plane using transistors. Let's take a look at how to implement an AND plane. Well, this is an NMOS OR. I know that in your logic course, you learned something called De Morgan's theorem, right? And what did that say?
Distribute the negative.
Okay, so you can reverse ANDs and ORs if you just reverse the polarity of the inputs and the outputs, right? So that means that if I have a NOR gate, and everybody agrees this is a NOR gate, right? If either of the inputs here are high, the output will be low. So this is a NOR gate here. I can turn a NOR into a AND by simply negating the input. What that's saying is that a NOR gate that looks like this is equal to an AND gate, right? And so all I have to put in this space over here is what? An inverter. And here, another inverter. So in the same way that I turned a NOR into an OR by putting an inverter on the output, I can turn a NOR into a AND by putting an inverter on the input. And lo and behold, I already have them. They're sitting right down here. So in fact, all I really need to do is pass these wires over here, like so. And let's say this is a term A. And I want to include, let's say this is a term B. And let's say I want to generate A and B on this wire here. Well, I take A inverse, I feed it into a transistor, put that transistor to ground, and hook it up to this wire. I take B inverse, hook it into a transistor, hook it to ground, and hook it up to the wire. And then I say by default, this wire goes to plus 5 volts. This is nothing more than this OR structure, kind of NOR structure, turned on its side. So if this is true or this is true, this output will be low. That's a NOR. But I'm inverting the inputs, so what it really says is if this is true and this is true, then this will be high. So this wire becomes A and B. In a similar way, I can generate different terms here. Let's call this X, and this is Y, and this is Z. Then this output here will be X or AB or Y or Z. And so in general, what's incredible about this is that using a NOR structure and another NOR structure with inverters on input and inverters on output, I can create logic of any type that I want in sum of products form. And all I really need is one kind of circuit here, which is this transistor switch, which can pull down, and a resistor, which by default pulls up, unless one of the switches pulls it down.
So how do you program that?
So that's a great question. Usually we have transistors everywhere in the plane, and the transistors are connected with tiny little fuses. And I can put the chip in a programmer, and I can burn the fuses out to get rid of the connections where I don't want them. That's one way to do it. The other way is that I can have this transistor have another transistor in series with it, like so, and this gate to be floating. Now, this transistor will only be able to act if this transistor on the bottom is on. And I can make this transistor turn on forever, or not turn on forever, by injecting charge onto that floating gate and letting it float forever. So in fact, I can program these things the same way I told you about You can program a ROM by using high voltage to tunnel charge onto that gate and then let go, and it'll be good for 10 or 20 years. Again, the typical lifetime we assume for these systems. Okay? And so there are programmable versions of this same thing. But it's really a neat structure. So if you want to, I'm going to give this out to you here, but you can go ahead as an exercise after class, or perhaps in the section, and implement where the transistor should go here for CO equals AB or BC or AC on this. Kind of neat. Those of you who have read this book by Tracy Kidder, I think called The Soul of a New Machine, have any of you guys read that? Yeah, it's a nice book, and it makes a big deal. It's about this computer they built at Data General. Of course, the company went down the tubes anyway, but at the time it was a big deal. And what they were able to do is they were able to use these PLAs to implement the logic in their system, whereas before everybody was hooking up AND and OR gates kind of by hand, one at a time. And so the innovation that let them bring their product to market fast was the heavy use of these programmable structures for the logic of the system. It turns out there's another type of device called a PAL, which is different than a PLA, and you'll see these advertised as chips that you can use. PLA stands for Programmable Logic Array. PAL stands for Programmable Array of Logic. It's just nomenclature, okay? For whatever reason, it became known that PALs were like this. The only difference is that a PAL has a fixed OR plane, okay? They only allow you to program the AND plane, and the OR planes are pretty much fixed. And they typically have flip-flops in them as well. And here's a picture of what a PAL looks like. It's kind of hard to read here. I think the picture in your notes, I hope, is a little better. If not, you can try to print that one out of the notes again, kind of big. Or you can go onto a website and look for the 22V10, which is a nice PAL. And what you'll see in the picture is here are the inputs here on the left-hand side, and they have an inverter and a buffer, and the signal and its inverse is sent down a wire here and then sent across a set of wires that go across like this. Wherever you want to, you can mark for transistors to be filled in on the array here. Those AND terms then go down here into fixed OR gates, and they provide you with some OR gates that are very wide, like these ones in the middle, and some OR gates that only have a few AND terms in them that are over here on the side. And then those outputs then go to a logic block that can have a flip-flop in it. And then the output of the logic block is sent back around and inverted, and then goes back to a horizontal wire like this again. Now, why would you ever have logic followed by a flip-flop going back to the logic? Where have you guys seen that before? Finite state machine, right? This is a circuit that allows you to program finite state machines. You could build a Coke machine inside of one of these circuits. They sell it as a tiny little chip. You put it in a device called a PAL programmer, and you type in what equations you want to be in the combinational logic of the device, and it enables various transistors that are in this matrix here. And then you say, do it. You quote-unquote burn the PAL, because, like I said, in the old days there were a fuse that would burn out for each of the bits here. And when you're done, you have logic and flip-flops, and this whole thing can function as a state machine. It's pretty neat. Well, there are newer devices that have come out after PALs and PLAs called Field Programmable Gate Arrays, FPGAs. And it's basically a realization that sum of products is not good for every logic function, in particular the parity function you saw before. And so what it is really is it's a C network that has within it lots and lots of wires that crisscross each other and little blocks that you can program inside the wires. And you can, inside those wires, you can have ROMs and PLAs and gates. And then you can program the interconnect for what gets hooked up to what. So I have a diagram, first of all, of what's inside of the logic block of one of these typical things. So typically, you have a few lookup tables over here. So there's 3 blocks. This takes 4 inputs and produces 1 output. This takes 4 and produces 1. This takes, I think, 3 and produces 1. And a bunch of multiplexers and stuff. And you can program all of these things. You can program what goes in the table here, what goes in here, what goes in here, what the state of the multiplexers are. And then it also has some flip-flops in it that you can use to hold state for a state machine. And this entire thing is like a raisin, and there are many raisins within the bread. And the bread is a bunch of wiring that you can program how the wiring gets hooked up to each other. And to just give you an idea of how amazing this is, this shows you basically the interconnect. Here's the logic block here, and here's all the wiring. You can program each one of the circles. You can make a connection or you can break it. Okay? And this structure is replicated over and over again, thousands of times. And you basically get an array of this structure in 2D. And you can program thousands, if not millions, of different bits within this thing to perform the logic function that you want to do. So it's a way of prototyping circuits to implement a function without actually having to wire up gates or to build your own special purpose chip. And in particular, sort of the high level view of this thing is here's the logic devices here, and here's the wiring that goes around them, and here's a switch matrix to hook up certain wires with other wires that are there. And I believe that that's the end. So the point of that slide is to show you that even for functions like the parity function, it is possible to implement them in a regular structure. It's just that it will not be the sum of product structure that you saw here before. Okay?